This module describes what takes place when you compile a program. You might think it's pretty straightforward. You sit down and write a piece of .c code, then you compile it, and suddenly you've got an executable program out the other end. Surely that's all there is to it. Well, I guess that is all there is to it if you like to think of it in a broad perspective, but I'd like to have now a look at the individual steps that make up the compilation process. So, you start with several .c files. It could be one .c file, it could be 100 .c files. It depends on the project and it's up to you. Now, the very first thing that happens is the pre-compilation phase, where the pre-compiler gets a hold of your .c files and processes all those hash defines and hash includes and hash if-defs and all those things that begin with a hash. In other words, all the text substitution occurs. So essentially a copy of your .c file is made, a sort of a temporary file which gets deleted after the compilation is over. And that temporary file contains the code that you wrote with all the comments removed and all the hash lines processed. In other words, all the text substitution. So it could be that a given .c file might be 100 lines of code, but it might include, via the hash include directive, say 3 .h files, each of which might be 1,000 lines long. So you might have 3,100 lines in the corresponding temporary file. This process is obviously the pre-processing phase of the compiler. That happens first. That is not really part of the true compilation. Next, those temporary files are then compiled, and you end up with object files. What is an object file? Well, it is, if you like, the machine code equivalent of the source file that you wrote. So in other words, you write something in a .c file. You write something that you can understand. The compiler then converts it into something that a computer can understand. In other words, machine code. That conversion process is known as compiling. So the second phase of this is the compilation phase, the true compilation phase. The files that come out the other end are called object files. And depending on what operating system you're on, they'll have different extensions. On a Windows or DOS operating system, you'll have a file that ends in .obj, obj being short for object. And on a Unix system, you'll probably have a file that ends in .o, again, being short for object. Finally, it's time to essentially group all those .o files together and form them into one project. This is done along with libraries. Any necessary library functions that you referenced, in other words, printf, scanf, strlen, and all those, they will all be included in the executable program. This is called linking. All these .o files and all the libraries are all linked together to form one big program. Now, if you're in a Windows environment, this will probably be a .exe file. If you're in a Unix environment, this will, well, it probably won't have any extension at all. It'll just be an executable program. As I mentioned before, this .exe file, or the executable program file, is usually considerably larger than all the .o files put together. And that's due, of course, to all the library code that you didn't write yourself, but you are taking advantage of. Anyway, this whole process, the pre-processing, compiling, and linking, is thought of as compiling. When you call the compiler to compile a bunch of .c files, you just treat it as one big process. I wanted to show you that it can actually be broken down into 3 smaller steps. When you have spent some time creating systems and programs using the C programming language, you'll become more and more familiar with the different elements of the pre-processing, compiling, and linking phases. I'll give you a little bit of a head start by going into some detail about those right now. First of all, let's look at pre-compilation, also known as pre-processing. The names are interchangeable. During the pre-compile phase, each .c file is pre-processed. Now, sometimes this is done in memory, and sometimes this is done in a temporary file. All the preprocessor directives, hash include, hash define, hash ifdef, hash ifndef, and so forth, they're all processed. In other words, it's just text substitution. Comments are removed. The only errors that you're ever going to get out of this are going to be due to incorrectly formed directives. For example, macros. You might have a macro that requires 2 parameters and you may only give it 1 parameter somewhere in the code. You're going to get an error message because of that. You will not get many errors out of the pre-compilation phase. There's very few things that can go wrong. Another example might be you might have a hash if-def that doesn't have a hash end-if. Or you might have a comment that doesn't have a closing comment. These are pretty much the only sorts of errors that you're ever going to get out of the pre-compilation phase. Next comes the compilation phase. This is obviously the guts of it. This is the part of the process where the code that you've written is examined to see if it actually makes sense. This is the true compilation. At the end of this, you will have a .obj file or a .o file, depending on what operating system you're on, for each .c file that you have. Oftentimes, if you only have one .c file, they actually don't ever create a .obj or a .o file. In other words, all you end up with is an executable program. That doesn't mean the compilation phase has been skipped. It just means that the .o file is treated as a temporary file and is usually deleted. During the compilation phase, every line of code that you've written is checked for syntactic and grammatical correctness. In other words, have you got a semicolon on the end of each line? Have you got a closing curly brackets at the end of each function? And so on. This is all the language syntax. If you call any functions, if you make a call to a function, the compiler will check that the call that you're making provides the right number of parameters and the right types of the parameters, and that the return value of that function is treated correctly. It does this by comparing the function call against the prototypes, if there are any. There may not be any prototypes. Now, this is very important to know this. What it does not do is check to see if the function actually exists. Let me give you an example for this. You might have a function called printf. Well, we do have a function called printf. You may misspell printf in the .c file that you're creating, and you may call it printf with 2 f's, say printf. And what's going to happen during the compilation phase? Well, it won't be able to find a prototype for printf, so it will just assume that you didn't bother to write one, and it will just assume that you called that printf function correctly. It isn't until the linking phase, which is the final phase, that it actually looks to see if there is such a function called printf. So you will not get an error message about that. It just assumes that that function must exist off in some library somewhere. You will get an error message, but the error message will come during the linking phase. In other words, any error message you get will be about the syntax of the language or the existence or non-existence of variables. In other words, you cannot use a variable that's not declared. However, you can use a function that is not declared. That's one of the strange inconsistencies of the C language. That was one of the things that got fixed up when they moved to the C++ language. In C++, every function must have a prototype. It absolutely must have a prototype. The final phase is the linking phase. During the linking phase, all the object code that came out of the compilation phase is combined, or, well, it's called linked, with any required object code from the standard C library or any other libraries that you may have chosen to use. Usually you have to specify to the compiler that you want to use certain libraries. It will obviously go and find the standard C library for you with the great wealth of functions that are in there, so you won't have to specify that library. However, if you want to use things like math functions or functions for creating menus on the screen or pull-down menus or boxes, that sort of stuff, graphics perhaps, you will probably have to specify which library you want to use that contains the functions that you've been referring to in your .c files. If you don't specify such libraries, the compiler won't know where to go and find those functions you've been referring to. Any errors that come out of the linking phase will simply refer to functions that simply don't exist. Either they don't exist in the library or it can't find the library. Or perhaps you've just simply misspelt the name. Something like that. Okay, so to help you understand the linking phase, we might just have a quick word about libraries. Okay, let's talk about libraries now. A library is a collection of compiled functions available to be used in any program. In other words, it's reusable code. Let's say, for example, that the standard C library does not include a function for joining two strings together, putting a space between them, and returning how long they are in length combined. Now, I know that's very contrived, and you could probably write one to do that, but that's the whole point. See, standard C library does not contain such a function, useful or useless or otherwise, so you can write one. Now, once you've written one, you might decide that that's the sort of thing you want to use over and over again throughout your programming life. You might write it this month, and then 6 months later, when you're coming to create a whole new, brand new program, you may say to yourself, didn't I once have a function that does that? The answer, of course, is yes. So you say to yourself, great, well, I'll just copy and paste it from that program into this program. Yes, you can do that. And I don't want to go on about it, but I hate copying and pasting. Sure, you can copy and paste it. So you copy and paste it into the new program. And let's say at that point you discover that there's a bug in it, or discover that there's a new feature that you'd like it to do that you didn't think of in the last program that you came up with. So you make the changes, and you fix the bugs or implement the new features, and the program works beautifully. Then you go back and revisit the old program because, well, maybe because you decided you needed to add a new feature to that entire program. And of course you realize that the changes were never made to that original program. The version of the string function that you changed was the second version. You never could be bothered going back and changing the original. Maybe there were time constraints or you had deadlines to meet, so you didn't bother to make that second set of changes. Well, the point of libraries is that you never need to make more than one set of changes. If you think that a function is going to be useful, I should say, in more than one program, you simply put that function into a library, or you create a library if you need to, that will hold that function. As time goes on, you'll find yourself with a vast library of reusable functions, functions that are just handy that in the sense that they can be reincorporated into all or any of the future programs that you may or may not write. Okay, so that's what a library is. In fact, it's the compiled versions of those programs. The actual source code is kept separate from the library. The library itself is stored in a file, and the file is usually just a collection of .o files that have been merged into one library file. So it's worth remembering that it's not a collection of .c files, it's a collection of object files. And you know what an object file is because I told you just recently. Obviously you can create your own libraries. Now, when it comes to actually using a library, you have to tell the compiler two things. First, you have to tell it the name of the library you want to use. You have to put that somewhere in the compiler's option on the command line or in the compilation options of that project that you're developing. Okay, I'll summarize that. You need to specify to the compiler the name of the library. You also have to specify to the compiler where to find that library. Now cast your mind back to include files. Remember I said you can include a file using the #include directive, and the compiler has an include path, which is a list of directories it goes and looks in to try and find that include file. Well, in exactly the same way, the compiler has a library path, which again is a list of directories that the compiler will go and search in to try and find the library that you've named. And that's pretty much all there is to it. If you understood it with the include path, then hopefully you'll understand it with the library path. The only difference is the include path is examined during the pre-processing phase, and the library path is examined during the linking phase. Anyway, that's all there is to it. Well, that's not all there is to it, of course. You can obviously go into more and more detail, but I think at this particular level of experience for you, that's all you need to know about compiling, pre-processing, linking, and of libraries.